Welcome back. We just talked about details of the hydrogen oxygen reactions and the explosive limits of hydrogen oxygen mixtures, and the details of hydrogen oxidation essentially, and then we discussed about carbon monoxide oxidation, and now we will consider general considerations of hydrocarbon oxidation. Now the most important reactions in a hydrocarbon oxidation is, as we have discussed, that is of course the chain initiation, that is the formation of HO2. H is, as we discussed, is a very active radical, and its formation is intrinsic and is very important towards further propagation of the reaction, because these active radicals attack further incoming fuel molecules and oxygen, etc. And then these two are the most important reactions, this H plus O2 going to OH plus O, and of course that is the key chain branching step, and the key heat release step is CO plus OH going to CO2 plus H. Now hydrocarbon oxidation is hierarchical. What that means is that whatever large your fuel molecule is, suppose you are talking about butane, propane, butane, octane, and dodecan, which is, as we discussed, is essentially a surrogate for or a representative fuel of jet fuels. So nevertheless these fuels does not react with oxygen, and it's does not directly undergo oxidation. What they do is that these large hydrocarbon molecules, they break down into smaller C1, C2, C3 fragments. Okay, now this initial fuel breakdown is very fast, hence these are not rate limiting. But the important thing is that it's essentially then, no matter how large the fuel is, of course there are complicated species formed, but essentially the most important part is essentially the reaction of these C1, C2, C3 fragments, and reaction of H, O2, OH plus O, and so on and so forth. So in a very large complex fuel, for example with N-dodecan, the methane chemistry is still very important, because methane chemistry is essentially governed by the C1 chemistry. Okay, and also like hydrogen chemistry is very important, because this kind of this H will be formed, and those will react with O2 to form OH plus O, and so on and so forth. So when you want to construct a big reaction mechanism of reaction mechanism of a big fuel, we first need to understand the reaction mechanism of the small fuels. That is why hydrogen oxidation is very important, CO oxidation is very important, and then next we will study methane oxidation, which is also very important. Of course methane is an important fuel in natural gas, as you know, and of course hydrogen is also a very clean fuel, and the hydrogen is even more important because you see it does not produce CO2, which is an important greenhouse gas, and which is believed to be which is of course known to be important for climate change. So because hydrogen does not produce CO2, it's very important as a clean fuel, but of course it has, you see that it behaves, it is explosive, and it's very strongly diffusive and explosive over large range of temperature and pressures, and that's it prohibits its large scale use actually. So once again the dominant we can say that the dominant high temperature chemistry is essentially governed by this H2O2 chain, and this dominant low temperature chemistry is governed by the HO2 is governed by this HO2 chemistry. Okay, so that is the idea that we will follow. So methane oxidation can be schematically represented in this diagram, where methane essentially goes to form COH3. So these diagrams essentially are that these arrows indicate the process that is more important, these thick arrows indicate a process which is more important, whereas these thin arrows this indicate the process which are less important. But we can will discuss this in more details rather than going to a schematic. So first important thing is that how does CH4 essentially breaks down. Once again the most important step is initiation, but before that we should say that there are two initiation routes. And so these we first talk about the initiation reactions. The first is the high temperature route for methane breakdown. So methane breaks down essentially by CH4 plus M goes to CH3 plus H plus M. Once again the formation of this H radical is very important, as we discussed. So because as soon as the H radical is formed, the key chain branching step that we saw, this H1 reaction in the hydrogen oxygen, so immediately that can happen, and that can attack the fuel, the oxidizer, the oxygen molecule, and it can form OH and O. And now this OH and O, this CH4 can react with H, OH and O, and O and OH and form CH3 into this thing. And again, but we see that parallelly, if we just consider this reaction, CH4 plus H becomes CH3 plus H2. Okay, So, this very energetic hydrogen radical leads to the formation of a less energetic methyl radical CH3. As a result, there is too much if you see the ignition delay correlations of methane, you will see that the methane comes with a positive exponent, that is, the more methane is produced, the larger is the ignition. The larger the concentration of methane, the larger is the ignition delay, which is counterintuitive because methane is a fuel, but because this hydrogen atom, this hydrogen, very energetic hydrogen radical that is produced, that reacts with methane to form this less energetic CH3, this becomes a retarding step, but these are the initiation reactions. The low temperature route is that the CH4 will reacts with O2 to form the CH3 plus HO2, CH4 plus HO2 goes to form CH3 plus H2O2 hydrogen peroxide, and hydrogen peroxide plus M goes to form this chain branching OH plus M. So, this is the low temperature route. Oxidation path. Now, what happens then is that then there is continuous stripping of hydrogen from this C meth here, from this as you see here, this CH3 is formed, okay, and this is essentially from CH4 it forms CH3, and from CH2 it will form CH2, and there is this continuous stripping of hydrogen, and eventually it will be oxidized by the CO, CO will be formed, and then CO plus OH will go to react and will form CO2 plus H. Okay. So, these steps will continue to basically strip the CH4 to CH3 and CH3 to essentially CO and CO then to CO2, and this is the oxidation path, and of course, a hydrogen, that is the H atom that is formed, will oxidize leading to HO2. So, this is continuous stripping path. But then there is also a growth path, because this you will see that if you consider the GRI methane reaction mechanism, that is pretty big in size. Okay. So, what happens is that the CH3 can also combine, and it can, in presence of a third body, it can form C2H6. So, from one carbon it forms 2 carbons. So, in the methane reaction mechanism, these larger molecules of this C2H6, these are also important, and this becomes essentially a part of the ethane oxidation path. And it can also form CH3 plus CH3, it can also form C2H5 plus H, and it can go latched onto the ethyl oxidation path. So, as a result, these hydrocarbon reaction mechanisms are not are complex, because on one hand you see there is stripping of H to form CO2 plus H, on the other hand you will there is also continuously there is also a growth path in which larger and larger molecules are involved, and eventually these larger molecules will be broken down into smaller fragments, and then they will again go to CO plus OH and go to CO2 plus H. Now, that goes about that is about methane oxidation. Okay. What about oxidation of larger or ignition of larger hydrocarbons? Now, we discussed what ignition delay time is, and that is a very important process, and but if you see the ignition difficulty, it essentially depends on 2 things, that is the CH bond energy. Okay, and you will find that methane is the hardest to ignite, followed by ethane, followed by propane. And this is what is shown here in this temperature pressure curve, that methane becomes explosive only in this regime at very high temperature and high pressure, whereas ethane is then follows then, and then propane is this shows a very complicated behavior. The complicated behavior of propane essentially comes from this can be characterized by 2 things. One is called the cool flame, and another is a negative temperature coefficient. Both are very interesting things, and we will discuss a little bit about that. And all as this is a region of cool flame, where essentially we will see that instead of a bright blue flame or the normal flame, we will see a blue in color if it is a premix flame, which essentially comes from the hydroxyl and the C2 radicals. But in a cool flame, you will see that there is a lot of emission by this formaldehyde radicals, and which gives that a very pale blue color. Okay, and this is different from the normal high temperature flames, as we will discuss later. And also the corresponding phenomenon in ignition delay is that this ignition delay of N-heptane, where you see this negative temperature coefficient, that is, if you increase temperature is increased in this direction. Okay, so in this direction temperature increases. 800, 1000, 1200, But so if you see that normally we think that if temperature increases, this ignition delay time will be just like this, that is after temperature increases, ignition delay time also increases, because it is clear that the chain branching reactions are promoted. Okay. But you see in these kinds of larger fuels like NHEP10 etc., this ignition delay first decreases, then again it increases, or it has a plateau region, then it decreases. So, this is called the negative temperature coefficient phenomena, but it happens at a very interesting range. You see this 700 to 1000 Kelvin, which is often the inlet, often the temperature at which fuel and air mixes in practical air breathing propulsion engines like in a gas turbine engine or in a scramjet combustor. Now, we need to know some rules about of essentially which bonds we are talking about. Bond energy, that is we said that methane is most least explosive at a given temperature pressure, and propane is most explosive because of the CH bond energy. The bond energy of CH4 is highest, and then it's less is you have C2H6 is has less bond energy, and then the C3H has even lesser bond energy. So the propane is more easy to break and easy to ignite. Now, the beta scission rule we need to understand is that the beta scission rule tells us that the oxidation of an aliphatic, that is this straight chain alkanes, is usually initiated by the abstraction of a hydrogen atom. As you see that what the stripping down of this hydrocarbons means essentially of hydrogen atoms is essentially by this hydrogen abstraction process. So, CH4 plus if you go into this reaction, CH4 plus M becomes CH3 plus H plus M. So, this is a hydrogen abstraction reaction where CH4 is stripped off from its hydrogen, and this hydrogen becomes a free radical, and so that it becomes free to react and go free to attack other fuel molecules. Okay. So, the oxidation of an aliphatic. So, then the question is that now if you have this kind of an methyl or a butyl group where you have this unpaired electron in this this is a propyl group, then or this propyl radical, then which CC bond is the weakest? The rule says is that the beta scission rule says that the oxidation of aliphatic is usually initiated by the abstraction of an hydrogen atom of the molecule yielding at a primary propyl radical, and the beta scission rule tells that the bond that breaks, the bond that will break is usually the one that is breaks is one removed from the radical side. So, this is the radical side. So, the most the bond that is most prone to break up is essentially the one that is one removed, that is not this one removed from the radical side, which is this one. Now, why? Because you see that invariably this pair presence of this unpaired electron essentially strengthens these bonds. The CC bond, which is about 100, these are in arbitrary units, but then in comparison then this CC bond becomes weaker, and as a result it is prone to break, and that is the beta scission rule. Okay. So, a CC bond is essentially weaker than a CH bond, but the CH dissociation has a higher A factor, and as a result this CC breaking happens at low temperature, whereas CH breaking happens at high temperature. Now, what is cool flame and NTC phenomena? As we have seen that when it comes to like propane and higher hydrocarbon, it shows something like there is a regime in which there is called a cool flame, and where it shows this NTC phenomena. Now, the explosion process, if we remember, it depends on the initial attack of the hydrocarbon molecules by oxygen and thereby through active radicals. Okay. The difference in the bond energies is translated into the difference in the activation energy of these reactions. Now, methane, as we have seen that previously, what we discussed is that the methane varies smoothly, ethane varies also smoothly, but higher aliphatic hydrocarbons, this cool flame, it has a complex behavior. Okay. It is a complex explosion PD diagram. It is this non-monotonic diagram like this. So, that is what is makes it interesting. So, why does it happen is that for hydrocarbon flames of propane and larger hydrocarbons in the low to intermediate temperature regime, increasing temperature can lead to slowdown in the reactivity of the mixture, and that is manifested by this pale blue emissions coming from formaldehyde. Okay. So, in this thing if we just take this take at a constant pressure, if we just have 5 stations at different increasing temperature in this regime map, what we see is that at point A there is no observational change in temperature, there is mild oxidation, this is not relevant for combustion. Then explosion occurs at point B, but it is characterized by this observation of pale blue emission characteristics of peroxides and formaldehyde. The green C2 and the blue violet CH emission are characteristics of the high temperature regime, and this is called the cool flame regime. Okay. And then once we increase it to C, increase in temperature slows down the reaction because of heat loss, and it is also because of certain production of certain other radicals that will come, and this is essentially the negative temperature coefficient regime. Okay. It is essentially the chain, as we will see, that is essentially the chain branching reactions that will be stopped, and as a result of this it becomes a non-explosive. And then as we increase it to higher temperature, it results in explosion because of the normal promotion of the chain branching reactions at H plus O2 goes to OH plus O at high temperatures. So, what is the mechanism of this cool flame and this NTC? Now, this is important because as we saw that even in the previous slide, in the Dodecan slide, if we go back now also that yeah, this is the slide that this is the NTC behavior. This was for N this was for normal Dodecan. Yes, as we remember that the Dodecan was essentially the surrogate fuel for kerosene. Okay. And this Dodecan shows this interesting negative temperature coefficient. Now, that is why it is important to understand the cool flame and this NTC phenomena, because this Dodecan or this large hydrocarbon shows this very interesting negative temperature phenomena at these temperatures of choice, which is this is about 1000 Kelvin and this is about say 900, 800 or 700 Kelvin. Okay. So, from that point of view, it is important to understand why this negative temperature coefficient happens and why this cool flame phenomena happens, because this is this regime corresponds to a very interesting regime from a aero propulsion engine, aero propulsion combustor point of view. And of course, as you know, the Dodecan is a surrogate of kerosene, of Jet A, and hence we need to understand why, what causes this. So, once again, to recapitulate, the negative temperature coefficient is that as your temperature increases in this direction, in this 1000 by T, this kind of representation. So, the temperature increases in this direction. So, it is normal to expect that as temperature increases, the ignition delay time reduces, right, because at higher temperature, of course, the reaction rates increase, and of course, as we have seen, the chain branching reactions also increase. So, it is reasonable to expect that at high temperatures your the ignition delay time will be less, and it happens also, it reduces as we see here. And for normal small hydrocarbons, for methane it is like monotonic, it goes straight like this. Okay. But you see here that for this Dodecan it first decreases and then it increases and then it decreases, and this increase and decrease with temperature, or this negative temperature coefficient phenomena, as we discussed, can be only explained by detailed reaction mechanisms and cannot be explained by global one step reactions. And we need to understand what causes this NTC phenomena because of its relevance to Jet A, and the temperature range is relevant in the gas turbine as well as in the scramjet combustors. This is where we were, that the mechanism of cool flames and NTC. So, both are essentially the similar mechanism. So, what happens is that initially of course, this RH we can represent R by like if it is Dodecan, R is essentially the formula for Dodecan is C12H24, but R essentially can be C12H23. Okay. With H, when that RH reacts with oxygen, it becomes R and HO2. So, this is the initiation step. Okay. And then this R can now react with oxygen in presence of a third body, and not directly in presence, the third body comes and hits the molecule slightly afterwards, and then it can form essentially this RO2 and this M. Now, this RO2 that is formed can now react with this RH, that is the actual fuel molecule, and form this peroxide molecule, that is RO2H plus R. Okay. This RO2H then can react with M, that is the third body, to form this RO plus OH plus M. The interesting thing is that this reaction, this RO plus OH, is because one radical gives rise to these two radicals, is essentially a chain branching reaction. Okay. So, that is, this is very, very important. Of course, this is also initiation reaction, and this is also exothermic reaction, which are also important. Okay. But now what happens is that at this is one way. Of course, now what happens is that if the temperature goes beyond 600 Kelvin, okay, instead of this reaction R2, there is another alternative reaction between R and O2. Okay. So, and that alternative reaction is this one, that is at beyond, at high temperatures, beyond, not at very high temperatures, but between 600 and 700 Kelvin, this R plus O2, instead of following this route, it can react R plus O2 and it can form an olefin and HO2. Okay. And this guy, this RH, then essentially can react with HOH plus HO2 plus RO, and it can form this sort of HO2, ROH, H2O2, etc. All right. Now, the thing is that because R3 is promoted and R2 is diminished, let us see what the effect the diminishing of R2 has. Now, if R2 is diminished, what we see is that if R2 is diminished, because essentially the reaction rate constant of R2 decreases with temperature. Okay, it is essentially a third body reaction. So, if R2 is diminished, this reaction is diminished, RO2, formation of RO2 is diminished. If formation of RO2 is diminished, you see that the formation of RO2H is diminished, a formation of RO2H is diminished, formation of RO plus OH is diminished. Okay. So, the chain branching step, the key chain branching step in this reaction mechanism is essentially diminished, and as a result, if the chain branching step is diminished, whether this R5 is diminished because of the diminishing of R2, you see that of course the reaction stops. Okay. The chain branching reaction essentially stops, and as a result the temperature does not rise. Okay. Or the ignition delays, the temperature, when the temperature rises between 600 and 700 Kelvin, sorry, when the temperature rises between 600 and 700 Kelvin, your ignition delay basically becomes bigger, because now you do not have an active chain branching reaction in your reaction mechanism. Okay. Now, does it continue forever? No, because when you increase the temperature to beyond 700 Kelvin, you see this H2O2 reacting with in presence of a third body and is forming OH plus M. Okay. So, this is another chain branching reaction that comes along, and as a result of which after 700 Kelvin the ignition delay temperature further can decrease. Okay. So, in this intermediate temperature range of 700 to 500 Kelvin, you get this thing if you plot it in 1000 by T, and this is tau ig, you get this kind of a thing. So, this between this range is essentially explained by this thing, that is in this range what happens is that up to this range everything was going fine, but after this, from this point onwards, your reaction 2 is diminished, and as a result of the thing the chain branching reaction is diminished, and but after this point, that is after about say 700 Kelvin, there is another alternative chain branching reaction that pops up, HO2 plus M going to OH plus M, and as a result your T ignition delay further can reduce.